Okay, let's take a look on my solution. So the first part, we want to do a standard scalar. So we create a standard scalar and then we want to fit the standard scalar with all the features except the column we want to predict. So we throw away that column and then we fit all the remaining features to the standard scalar. The next part, we want to use scalar.transform. We are transforming all the features into the scaled features, and eventually we will have a nested list. So the scaled features will be a nested list for now. And we say we don't like that, we want to build a data frame. So to do that, we first grab all the possible names from all the columns in the data frame, and then we want to throw away the column we are predicting because that is not a feature. So we throw that away, and then eventually we have those columns. Okay, so then we try to reassemble a scaled data frame. So I'm gonna make use of the nested list scaled features, and then the columns equals columns. So the columns will be the columns we just created here. So this is a data frame we just created, and remember we don't have the not fully paid column, so they are all features. Okay. So after that, this is a beautiful data frame with all the features standard scaled. So the next part, we want to do a train test split. So X will be all the scaled features and Y will be the loans with the column not fully paid. And then we want to do the train test split. And after that, we create a k-nearest neighbor with the k as a 1, and we fit the k-nearest neighbor with the x train and y train, and then we do the prediction, and we create the confusion matrix. So if you take a look on this one, so what do you find? So that is, remember, each of the column is a predicted label, right? So this one and 2084 and the 350, they are the values predicted to be 0. And then for 93 and 347, they are the columns, they are the values to be predicted as 1. So 1 means not fully paid as a true. So what does this number mean? So this number means we predict those samples to be not fully paid as a 1, but actually they are a 0. So that is the number of false positive, right? So we say they won't pay me back the money, but actually those people did pay me back. And how about this one? This one is, well, we predict they are 0, but actually they are a 1. So we predict the not fully paid to be a 0, and I'm guessing the 0 should be a false. So not fully paid to be a false, which means this money will be fully paid back to me. That is the prediction. However, it is not correct. So for those number 350, I'm gonna lend my money to those people, but those people won't pay the money fully back to me. So the next question is the part we have discussed. So false positive and false negative. So in our evaluations, we are evaluating those two to have the same weight. But think about that. Is that really true? Those are false positives. The model says I shouldn't lend my money to those persons because they ain't gonna pay me back. So the decision is probably I'm gonna follow that. I won't lend my money to those people, even though they can pay me money back eventually. Well, it's not a big hurt. It's not a big pain. But for those people, the false negatives. So the machine learning model says I can safely lend my money to those people and they will pay me money back, but the machine learning model is wrong. And for those money, I'm gonna just lose it. So no one is gonna pay me back. And Lending Club, this website is not cover my loss either. So in this case, the false negative is gonna be really much more expensive than the false positives. So when you are evaluating this kind of machine learning model, you have to pay attention to that, because the false positives and the false negatives, the loss could be different. Okay, so and after that, if you want to, you can change this number to 3 or to 5 and you can get different things. So that's it for today's lecture. So if you want to do a very quick sum up, the first thing is, remember k-nearest neighbor is very sensitive to the scales of the features. And if you observe the ranges of the features are not the same, remember you need to do standard scalar, because later you are going to use distance matrix. So the next thing is, well, if when we are trying to deal with the categorical features, and remember you have to do one hot encoder, and for the one hot encoder you can always safely drop one of them, because the remaining n-1 features can be predictors of the one you just dropped, so you are still safe. Okay, so that's it for today's lecture, and I will see you guys tomorrow. Bye.